Doing the complete formula then, we can now expand the P&L formula for the market maker. And all of these will be somewhat familiar to what we saw earlier. First of all, we have the change in stock value, which looks no different from the earlier representation. It's really the change in the option value where we've now replaced the original change, which was, you may recall, CT plus H minus CT. We'll replace that change in the option value with a Taylor series approximation. And what we see is we have the delta gamma terms and we have the theta term. Notice we have a negative in front of the theta. So for the P&L of the market maker, the effective theta is positive because theta is negative and we have a negative in front of it. And then finally, we have interest expense. RH is just an approximation for the interest expense. This is another example of the actual interest expense is e to the RH minus 1 times the borrowing. And if you approximate e to the RH minus 1 using the approximation we saw, you get RH. Notice that the theta and the delta and the gamma, they're all calculated at time t with the given stock price. So each one of them should have a subscript and to denote that the time at which we calculated them, because they all change over time. And we just, for notational simplicity, didn't have that. And then I already made the point that the interest approximation is, again, using this formula. So if we now look at the mathematics of delta hedging, if sigma is our annual, again, we're returning to this notion of what happens if stock prices move one standard deviation. So if S1 is indeed S0 with one plus or minus standard deviation based on our lattice, this is the formula. Now again, notice going from here to here, I use that exponential approximation. And going from here to here, I'm basically acknowledging that H is small compared to square root of H. And there's a table we'll see later in this analysis. But when you're dealing with continuous time finance and the approximations with the binomial model, the intuition is that the drift term only looks important when H is relatively big, because then H is perhaps bigger than square root of H. But the smaller H gets, the smaller H looks compared to square root of H. And what happens is as H goes to 0, it's the square root of H term that dominates. The H term you can throw away. It almost has no effect. And so with this value for the change in, if we just now substitute that this is the epsilon in the formula, we get that the P&L can be written this way. The P&L is equal to minus, we have a bracketed expression, times H. So the P&L is negative, H is the time interval. But notice that inside this parentheses are all the terms evaluated at t. They don't reflect H. The H is a multiplicative factor that gets factored out. And what we see is the volatility of the stock and squared. We have a gamma, we have a theta, we have delta, and we have the call price. And what we're going to see using the Black-Scholes analysis in a moment is that what's in parentheses is theoretically equal to 0 for a call option. Namely, that this equation is approximately what the P&L is when the stock price moves by one standard deviation. And, in fact, this expression is identically 0. So what we have then is concluding that when the stock prices move one standard deviation, in fact, the P&L is approximately 0. And that's what we saw in the numerical illustration earlier. So in the parameters of our problem, where we can actually look at the day one delta, gamma, theta, and so forth, we actually calculate a P&L to be 0, at least to a couple of decimal places. And it's the Black-Scholes analysis that tells us that actually when the change in the stock price is in fact a multiple of the standard deviation of stock prices, this is always true theoretically. And we'll see that coming up. Here's a numerical illustration of the P&L formula where you look at different values of the change. And what you can see is this middle value where the P&L becomes 0 is for a stock price move of around 63 cents, and 63 cents is exactly one standard deviation, one daily standard deviation. So numerically we see it borne out, and we'll have some theory to show why this is true later. We already have an approximate explanation using a binomial lattice, but in fact we can also defend this conclusion using a more formal analysis using Black-Scholes mathematics.